In the subarray sum problem, we realize that adjacent subarrays in fact have a significant overlap. For example, this subarray here and this subarray here, in fact, two items are common. If we were to make it more precise, for a subarray of size k, in fact, k minus 1 items will be common between two adjacent subarrays. Now, this is significant. Remember, if k becomes large, then more is the overlap. So, for example, if let's say I looked at a window of say 7 items, so I'm looking at 7 items. Notice that 6 out of these are in fact common. Now, this is a very, very, very crucial insight because this will lead us to significantly simplify the entire problem. As you can see, given that there is overlap, in fact, when I'm finding this sum, the sum of this subarray, I can reuse some of the work that had been done to form, in fact, this sum. And the way we do that is, well, I can set 2 pointers. Remember, this is a sliding window. So I'm interested in not just the pointers, but in fact, everything in between them. So I view this as a window between these 2 pointers. I find the sum of the first subarray. I do this much work, no problem. But once it comes to finding the sum of the second subarray, all I need to do is to take out this guy, which is L0, and in fact add this guy, which is L3. Now extend this idea further. If my k was larger, no problem. My first time I found the entire sum, no worries. But subsequently, there is a significant overlap. I don't have to do these summations because they have already been done. All I need to do is to remove so L0, which is the zeroth item, and add in the seventh item. Now, if we were to just generalize this a little bit, basically what we are saying is that, look, we have a window which is bounded by these 2 pointers. I'm going to, slide this window across. Every time I slide, I will have an item which is leaving. I'll have an item which is joining. So if I have done the sum one time in the beginning, so I do the original sum one time, I do the entire thing, but having done that once, all I need to do is to take care of these two items. The one that is leaving, I can subtract that. The one that is joining, I can add that. So it's L0 and L7. In this case, because K is 7, I can keep moving these pointers across until I reach the end of the list just by taking care of the item that is leaving, item that is joining, and I would have in fact found all the sums, and hence finding the max becomes then, let's say trivial from there. So the point here is that, look, I am going to view this subarray as a window of data bounded by these 2 pointers. The separation of the pointers determines the size of the window. So it's going to be right minus left plus 1. Again, remember, this is, for example, 0, 1, 2, 3, 4, 5, 6. So right is on 6, left is on 0. The size of the window is 7. So basically, 0 minus 6 plus 1. 6 minus 0 plus 1, sorry. For the very first subarray, I find the sum by adding up all the items, no problem. But for every subsequent subarray, we do not need to find the sum of all the items. In fact, we just need to look at the previous sum. We can subtract the item that is leaving. We can add in the item that is entering, and hence we can then keep finding the new sums and finding the max of all that. So this is the intuition behind it. We are going to write this in code. Very, very interesting. We'll see how the complexity comes down from being O of n squared to O of n. In the next few videos, we are going to look at the code to implement this because that also is interesting in its own right. But I hope you found this interesting. Do look at our website www.yby.in. We always go in a step-by-step systematic manner, analyzing every part of the code in detail, and hence we always enjoy coding. Take care. Thank you so much. Bye-bye.